Hi, everyone. Welcome back to the final section of Chapter 2. This chapter is very long. It's got a lot of really important information about functions that you need or you can't do a lot of other stuff in mathematics. So long, tedious, but it is finally coming to an end here with inverse functions. So the first thing we're going to talk about are one-to-one functions. Now, one-to-one functions are similar to functions. We're going to think about them kind of similar, except we're going to get one extra rule. So if you think back to 2.4, when we talked about functions initially, the rule we had is that every x has to go to 1y. Every x has to be used, and every x can only be used once. We had no restrictions on the y's. However, what we now introduced in 2.9 are one-to-one functions. And one-to-one functions mean that every x goes to one unique y. So in regular functions, we allow all the x's to go to the same y if we wanted to. If 1 goes to 1 and 2 goes to 1 and 3 goes to 1 and 4 goes to 1 and 5 goes to 1, that's fine. As long as every x is only used once, we're good. But now in one-to-one functions, we're restricting that every y can only be used once as well. So this is going to be the last time in this chapter that we're going to go to the whiteboard. So let's do that one more time. Okay, so for the last time here in chapter 2, don't forget that when we did functions initially, we allowed ourselves to do 1, 2, and say something like that every x was used and every x was only used once. The second we did something like this, where 1 was used twice, that wasn't a function to begin with. The second that, say, 3 doesn't go to anything, that also isn't a function to begin with. Don't forget that for just functions, every x has to be used and every x can only be used once. Now, when we're talking about one-to-one functions, the extra restriction we have is that every x can only go to one unique y. So now we're only allowing y's to be used only once. So in this example that you see on the screen right now, this isn't one-to-one because 4 is used twice. This isn't one-to-one, this is 2-to-1, right? 2 x's go to 1 y, 2-to-1. So instead, what we can do is if we have something like this would be 1-to-1. So it's as simple as that. It doesn't even need to be in that order, right? For example, 2 can go to 6 and 3 can go to 5. As long as every x is only used and every y is only used, this is a one-to-one function. So just wanted to show this off. Now we're going to get back to the presentation for the rest of the lecture. Okay, so now we're back. Just wanted to show the correspondence diagrams. That's what those little circle things are. But now let's continue. So for example, f of x equals x is 1-to-1 since every x goes to 1y. There's no way that you can make two different x's equal the same y value. However, x squared is not 1-to-1 because -2 squared is 4 and +2 squared is 4. Two x's go to one single y value. Okay, well, two ways to determine if a function is one-to-one. We have an algebraic way and a graphical way. Algebraically, what we're going to do, we want f of a equals f of b to lead to a equals b. If this is true, then it is one-to-one. Graphically, how we do this is the horizontal line test. So vertical line test says if our vertical pencil covers any 2 points at once, it's not a function. And likewise, horizontal line test would say if your horizontal pencil covers 2 points at once, it's not one-to-one. Now, the big thing here to note is that a function can be a function, and it might just not be one-to-one. That's totally okay. We'll come to what that means to not be one-to-one in just a moment, but just because something isn't one-to-one doesn't mean it's not a function. It just means it's not a one-to-one function. So just something to keep in mind. So let's just do some examples of determining if something is one-to-one. So let's say we have the function 4x minus 4. What we want to do is start with f of a equals f of b and get it down to a equals b. In other words, we want to solve for a. If we get a equals b, then your function is one-to-one. Otherwise, if you get anything else besides a equals b, it is not 1-to-1. So f of a says plug in a, f of b says plug in b. And what we can do from here to solve for a, we can add 4 to both sides. Well, that gets rid of both of the 4s. We can divide both sides by 4 and we get a equals b. So we got a equals b. In the event that f of a equals f of b leads to a equals b, your function is 1-to-1. This is the result we want. Now you might be wondering, how on earth could we possibly get anything besides a equals b in this way? Well, let's do another one. Let's do x squared minus 2. Well, again, we start with f of a equals f of b, so we're going to plug in a and plug in b. We're going to add 2 to both sides, and then if we want to solve for a, we need to take the square root of both sides. But don't forget from the entire chapter solving equations that when we take the square root of both sides, we pick up plus and minus. Okay, so the square roots cancel out the squareds, but we now get a equals plus and minus b. This is not our desired result. Our desired result is a equals b, and we got something that isn't exactly a equals b. In that case, we would just say our function's not 1-to-1. X squared minus 2 is still a function. It's just not a 1-to-1 function, and that's okay. So the reason this is true is because f of 2 would be 2 squared minus 2, 4 minus 2, which is 2, and f of negative 2, well, negative 2 squared is also positive 4, and we get 2 that way. So even though that negative 2 and 2 both went to positive 2, the two values weren't equal to begin with, so that's not allowed for 1-to-1 functions. So that's all that is. F of x equals x cubed plus 1. Well, you might think that every exponent now is going to fail. Well, let's see. Plug in a, plug in b. Let's subtract 1 on both sides. And let's now take the cube root of both sides. But don't forget that when we take square roots and even roots, we pick up a plus and minus. But when we do cube roots, fifth roots, odd roots, we do not pick up a plus and minus. Well, in this case, the cube root and the cubed cancel each other out on both sides, and we get our desired result, a equals b. So you probably already start to see that anything that is even power might not be 1-to-1, whereas odd powers will. We'll look at those graphs in just a moment. Let's say we have f of x equals 7 over x plus 2. Well, here's what we're going to do. Same thing, f of a equals f of b. And what we're going to do is cross multiply, right? We haven't really done a whole lot of cross multiplying in this class, but let's do 7 times b plus 2 equals a plus 2 times 7. Let's divide both sides by 7, and let's subtract 2 on both sides, and we get b equals a. Okay, I know this isn't exactly a equals b, but it is basically the same thing, right? A equals plus and minus b is fundamentally different from a equals b, but b equals a and a equals b are saying the exact same thing. So this function would be 1-to-1. So just to show you graphically how these would work, again, horizontal line test says if your finger, your pencil, covers 2 points at once, it's not 1-to-1 when it's held horizontally. So here's 4x minus 4, just a line. Notice that there is no horizontal line that covers this graph at more than 1 point. X cubed plus 1, odd roots. Oh, yeah, okay, that's not so bad. But the second we got x squared minus 2, well, now we have plenty of horizontal lines that cover more than 1 point at once. So there you go. This would fail the horizontal line test. Again, x squared minus 2 is a function. It passes the vertical line test, but just because it is a function doesn't mean it's necessarily a 1-to-1 function. And there's 7 over x plus 2. Rational functions, we'll spend a little bit more time with in chapter 3, but point is not quite anything of interest. So, all right. Well, so now we know what 1-to-1 functions are, but the entire purpose of the section is for inverse functions. So let's say we have the function x cubed plus 1, and when we plug in 2, we get 2 cubed plus 1 which is 9. Okay, nothing really surprising there. So 2 goes to 9, but how do we go from 9 back to 2? Well, that would be the process of taking inverses. Now, the whole reason we found one-to-one functions is because if a function is one-to-one, it has an inverse. So only one-to-one functions are what we call invertible. So if it's not one-to-one, it doesn't have an inverse. Likewise, if it has an inverse, the function is one-to-one. So the whole reason we spent all this time finding one-to-one functions is to determine whether or not a function has an inverse. Okay, we write the inverse of f of x as f inverse of x. This is not reciprocal. This is not raised to the -1. This is saying f inverse of x. And that's very different from anything else. That -1 has no algebraic property besides denoting an inverse function. Okay, so how do we find inverse functions? Well, it sounds like it could be a complicated process, but it actually isn't that bad. So to find the inverse, we have 4 steps. One of those steps is going to have multiple steps, but in general, 4 steps. Step 1, you're given f of x. Change f of x to y. You'll see why we do that in just a moment, no pun intended. You'll see why we do that in just a moment, because working with f of x can be kind of complicated for no reason. However, we know that f of x and y are the same thing, so it doesn't hurt us at all to replace f of x with y. Step 2, we're going to exchange the locations of x and y. And what I mean by that is literally wherever we see x, start writing y. Wherever we see y, start writing x. So we are literally taking all the locations and flipping them between x and y. And this is the new step to this section. So next step is to solve for y. You started with y equals something. So then after you change x and y, you get x equals something. Well, we want to get our answer back to be y equals something. Okay, so our step 1 was to get y equals. We solve for y. We have a new y equals, but those y's aren't the same. This y came from f of x. This y will be f inverse of x. Okay, so let's get right into it. F of x equals 4x minus 4. Step 1, replace f of x with y. That's the important part. That's the important start. Step 2, wherever we see y, write x. Wherever we see x, write y. So instead of y equals 4x minus 4, we are instead going to have x equals 4y minus 4. Literally switched x and y. Step 3 is going to be your longest step every time. Step 3 says solve for y. We want to get this y by itself. How we do that? We can add 4 to both sides. We can divide both sides by 4. And look at that. We got y equals. However, we have one more step. Notice that this is y equals 4x minus 4, and this is y equals x plus 4 over 4. We have y equals 2 completely separate things that are not equal to each other. In that case, this y was originally f of x. This y is f inverse of x. And that's always going to be your last step, changing y to f inverse after you have completed the process of inverting the function. Okay, let's do the same thing for x cubed plus 1. First step, change f of x to y. Step 2, wherever we see y, write x. Wherever we see x, write y. So instead of y equals x cubed plus 1, we are instead going to have x equals y cubed plus 1. From here, we're going to solve for y. We want to get this y by itself. So let's subtract 1 on both sides. Let's take the cube root of both sides. Don't forget taking cube roots, taking fifth roots, and taking odd roots. Do not add plus and minus, so nothing's wrong here. Okay, and yeah, we have y equals cube root of x minus 1, but this y is different from this y. This y was f of x. This y is f inverse of x. Okay. Well, we said this function here, x squared minus 2, wasn't one-to-one, so it doesn't have an inverse. But let's see why. Okay. So step one, if this was to be inverted, let's say f of x equals y, step one. Step two, switch x and y. Step three, let's solve for y. So let's add 2 to both sides. And let's take the square root of both sides. But don't forget that when we take the square root of both sides, we get plus and minus. Okay, and here's where something is very wrong. This isn't a function to begin with. If it's going to be a function, if this thing right here is a function, that means when we plug in 1x, we only get 1y back, right? Vertical line test, definition of a function. We can only get 1y value for every x. So if we plugged in x equals 2, 2 plus 2 is 4, square root of 4 is 2, and we get plus and minus 2. 1x went to 2y's. That's completely illegal in terms of functions. So the inverse isn't even a function to begin with. So if the inverse is not a function, that function just doesn't have an inverse. Or, we already knew that because of the one-to-one thing we checked earlier. So if you try to invert a function and if it gets you to a point that it doesn't, it's not a function, that's fine. It just means it wasn't invertible to begin with, and that's very much okay. Alrighty. Well, what if we started with square root of x plus 2? Well, if we start with square root of x plus 2, we can find its inverse. Don't forget, x squared minus 2 isn't 1-to-1 to begin with, but square root of x plus 2, if you were to graph it, that is 1-to-1. So let's see what happens. Switch f of x to y, switch x and y. Let's square both sides, and let's subtract 2. Okay, well, you're probably wondering why, not literally why, x squared minus 2 is now the inverse. Well, what it comes down to is the domains of these functions. So, for example, the domain of square root of x plus 2 is negative 2 to infinity. There's only one branch to this square root of x plus 2. Well, if the domain is negative 2 to infinity, that means that this is restricted to something similar. If you start with something whose domain is all real numbers, you can have a problem at the end. But if you start with something that has a more restrictive domain, then you will get to a point that is okay. So kind of hard to explain here without showing a picture. Long story short, don't worry. In most cases, it's usually noted like, okay, when x is greater than negative 2 or something to that effect. So it works this way algebraically, but there are some quirks at hand that most likely you don't have to worry about. So instead of y equals, we have f inverse. But again, it just comes down to the definition of the function we started with versus the function we ended with, right? Starting from square root of x plus 2 is different than starting from x squared minus 2. Okay, let's do a weird one. F of x equals 7 plus the cube root of x minus 6. Step 1, switch f of x to y. Step 2, switch x and y. Step 3, solve for y. Okay, let's get the root by itself. So let's subtract 7 on both sides. We can get rid of this root by cubing both sides, right? Cubing, not a problem at all. And then we can add 6 to both sides. All right, well, this is pretty okay. Well, instead of y equals all of this y is different from this y. So we're going to change this y to f inverse. That's it. Nothing scary at all. Let's do the rational function, right? We did that earlier. We found it to be 1-to-1, so let's find its inverse. Okay, step 1, switch f of x and y. Step 2, switch x and y. Step 3 is to solve for y, and we really got to get back into our toolbox of solving for variables like we did in chapter 1. So, well, first things first, we got to get y out of the denominator here. This is kind of a problem. So why don't we multiply both sides by y plus 2? Okay, well, this y is stuck inside the parentheses, so why don't we distribute x? X times y is xy, x times 2 is 2x. Well, we want to get y by itself, so why don't we subtract 2x on both sides and then divide by x. if this was 5 times y, you would divide by 5. So just because this is an x, we can still divide by x. Okay, not so shabby. This y is different from this y. We have f inverse. Just be very careful. This isn't technically the only way you could do this. You could actually divide by x here and then subtract 2. Your answer would be equivalent, but just something to keep an eye out for. Okay, let's do it where we have x's in both cases. Oi, all right, kind of scary looking. That's fine. Step 1, switch f of x to y. Step 2, switch x and y. But this time, we're going to switch it twice, right? X appears twice, y is going to now appear twice. All right, well, kind of an issue. We got multiple y's to deal with. Let's start by multiplying both sides by y minus 5. And let's again do what we did in the last slide and distribute this x. And now notice this. We have xy here and a y right here. We want all the y's to be together. So what I'm going to do is I'm going to subtract this y on both sides, and I'm going to add 5x to both sides because we don't want the x's on the same side as y. All right, now that all of our y's are on one side together, what we can do is factor out y. Okay, not so shabby. And now, if this was y times 5, you would divide both sides by 5. However, no different. Even though this is y times x minus 1, we can just divide both sides by x minus 1. And now this new y is f inverse. Okay, not super scary, but this might be, funny. Memes, yeah, woo. All right, well, just some results of inverse functions. Not going to spend a whole lot of time doing this, but just to show you some things. If f of x is 1-to-1 and f inverse is the inverse of f of x, then here's something about domain and range. This is interesting. The domain of f of x is the range of f inverse. And that's actually kind of interesting. Likewise, the range of f of x is the domain of f inverse. Oh, that's kind of neat. Well, kind of think about this because when we were doing step 2 literally said switch x and y. Well, x is like domain, y is like range. So when you switch x and y in that step, you're changing the domain and range of f of x with itself, right? The domain became the range, x became y, and the range became the domain, y became x. So that's kind of interesting. Likewise, since we're switching x and y, this is technically a reflection over the line y equals x, which is pretty neat. So if xy is a point on f of x, then yx would be a point on f inverse. So for example, if 3, 4 is a point on the original function, then 4, 3 is a point on the inverse. Also, inverses undo their original functions. So the inverse function property says that f inverse composed with f gives you just x for every x in the domain of f of x, and f composed with f inverse also equals x for every x in the domain of f inverse. So that's why we needed to talk about compositions in the last section before we got here. Okay, just some very silly looking examples. If f of 3 equals 5, then f inverse of 5 is 3. Yeah. If f inverse of -1 is 7, then f of 7 is -1. F inverse of f of 500, assuming 500 is in the domain of f, well, that's just 500. And assuming 2000 is in the domain of f inverse, f of f inverse is 2000. Very exciting. Okay, well, if we wanted to graph the inverses, you could find the inverse and graph it, or even easier, if you already have the graph of the original function, all we need to do is reflect over the line y equals x. So how we do that is take all the x's, make them y's, make all the y's the x's, or in other words, just flop the coordinates. 2, 4 will become 4, 2. 0, -4 will become -4, 0. And there is the graph with its inverse. X cubed plus 1, switch all the coordinates. Negative 1, 0 becomes 0, negative 1. 1, 2 becomes 2, 1. Okay. Well, we said x squared minus 2 is not invertible. We've now found it twice. It wasn't 1-to-1. Its inverse wasn't a function. Well, if we tried to do the same thing here, switching all the x's and y's with each other, we would get this. Well, this doesn't pass the vertical line test. So yeah, that's a different issue. So again, some more proof that if something isn't 1-to-1, its inverse, whatever it might be, is not a function. Okay, 7 over x plus 2. This is what the original graph looked like. When you invert it, when you switch all the x's and y's, it's actually pretty similar. Just another weird example for some obscure graph that we have here. Again, just switch all the x's and y's. -5, -5 will just stay -5, -5. But 0, -3 will become -3, 0. 3, 1 will become 1, 3. And 6, 5 will become 5, 6. Okay, and last but not least, going back to domain and range, if we think all the way back to 2.4 when we practiced finding domain, I said finding domain, very easy, but finding range is a lot more difficult. Well, here's finally the time that we can find range. Now, the only sad part is that we can only find range of 1-to-1 functions. This doesn't work for just any function. Function has to be 1-to-1 for us to find the range. Well, we saw a couple slides ago that the range of a function is the domain of the inverse. So if you want to find the range of a 1-to-1 function, you take its inverse, you take the domain of the inverse. So let's find the range of 3 over x minus 6. Well, y equals 3 over x minus 6. X equals 3 over y minus 6. Multiply both sides by y minus 6. Distribute x. Add 6x, divide by x. So the inverse is 6x plus 3 over x. And what we're going to do is find the domain of the inverse. Again, domain of the inverse is range of the original. Okay, domain of f inverse, where is this defined? Everywhere the denominator does not equal 0, everywhere that x is not equal to 0. So the range of the original function 7 over x plus 2 is, or not 7 over x plus 2, 3 over x minus 6 is -infinity to 0 and 0 to infinity. So that's how you can find range of 1-to-1 functions. And that's finally the end of chapter 2. So a lot of information here in chapter 2, lots of small things, right? For the most part, this section wasn't too crazy. It was introducing this switch x and y step, and then it was really just a lot of algebra to finish up. So with that said, next up is one section in chapter 8 for our course that kind of goes along with solving equations and graphing a little bit, and then we'll jump to chapter 3 after that. And chapter 3 will be the last section, last chapter of the algebra course that these lectures are for. So until then, bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.